Good morning, everybody. I hope everybody's enjoying this year's Center for Acoustics and Vibration workshop. How many people made it to the reception last night? All right. Well, we'll have I hope that you all had a chance to talk to the students and to look at their posters. And if you filled out an evaluation form, we greatly appreciate that. I get to work with a lot of these students, on a regular basis, and I'm still always amazed with the work that they're doing and how well they can present that work and represent the work going on here at Penn State, the CAV, and for our sponsors. So they deserve a good round of applause, even though I don't think only a few of them have made it here at this hour. It's still early by the student clock in the day. Well, we have an exciting second day of the workshop here today. We're going to start with, I'm Karl Reichard.
Hi, can you hear me?
No. And the graduate program in acoustics, and I'm going to be emceeing this morning's session. We're going to start with a couple of technical group presentations. From our adaptive structures and noise control group, from our Rotorcraft and dynamics group. We're going to have a special topic on urban air mobility vehicle noise by Dr. Greenwood. And then I'll present an update from one of our newer groups, the AI and machine learning group, that we started up as a result of a roundtable discussion that we had several years ago at the fall workshop. We'll take a coffee break, although please feel free to get up and avail yourself of a coffee and treats there during the sessions. We'll have a couple talks on machine learning and their applications in both failure prediction and also in additive manufacturing, which is a very big research effort here at Penn State, as well as within the Applied Research Lab. Then I'll give a presentation on some updates from our Systems and Structures Health Management group, along with a special topics presentation by Jacques Rivera on ultrasound for geoscience applications. We'll have a lunch again in Alumni Hall like we did yesterday, and then when we come back from lunch, we have a couple of more presentations. There's some exciting things happening on campus. Those of you who have been here before and toured our facilities have probably heard time and again how eventually we're going to get rid of Hammond building and build new buildings. Well, that's actually happening. So we're building new buildings. Whether we'll ever actually get rid of Hammond building or not, that remains to be seen. But we've got a lot of exciting construction going on West Campus, and that's going to include, when it's completed, a new tour for a new facility for the CAV and a new home for the acoustics program, as well as many of the other programs in the College of Engineering. And Dwayne Rush from our Office of Physical Plant will be here, and I'm sure he'll show some nice animations of walkthroughs. They have a great presentation online. If you're a Penn State alum or just interested, you can do a virtual tour of some of the things that they're doing in those buildings and the whole design process that went into coming up with that building design. Then we'll have a presentation on our acoustics metamaterials group and a presentation by one of our international liaisons on noise control research using passive and active materials. And then at the end of the day, before we adjourn, we will announce the winners of our student poster competition. So without further ado, I'm going to turn it over to Dr. Jin Ning. He is going to be presenting for Jose Palacios on our adaptive structures and noise control group. Thank you.
Make sure everyone can see me and hear me. Good. All right. All right. Can everyone hear me on Zoom? I think we're good, probably. All right. It's my pleasure to present my work to represent the group of adaptive structures and non-functional structures, and I'm grateful that Jose gave his time to me so I can share my work with you. So as you can see from the title, so as you can see from the title that I'm going to talk about some space structures that can morph, and the structures are multifunctional, and I will talk about something about electronic skins. But let me just give you a really quick overview on the morphable or deployable space structures. And the structures on the very left, on this one. So that is a solar array called the roll-out solar array. And it is very interesting because the solar array was deployed using these two reverse commenter tape like structure. So it's a very novel structure. And that was demonstrated in 2017. And actually now the International Space Station has several pairs of these solar arrays. So actually here I have a much smaller model for this type of deployable structure. You can see that I have this small bag and I can fold it into this small package. And Fatica, you can see it's really small. It's really small. It's just a small structure, and I'm going to deploy it. And you make sure that the audience in the Zoom room can also see me. All right, so I can see it. So it can self-deploy by releasing the strain energy stored in this tip spring, tip mirror-like structure, and it can extend to this 4 feet long boom, right? So you can see that is what I meant by deployable or morphable structures, and it's just a single piece of structure which can be folded into this very compact configuration, and it can stay there, then it can deploy, right? Of course, the structure here is a little bit different from this one. I will talk more about this one later. And the structure on the right side is the sunshield of James Webb Space Telescope. And I was really nervous when I was watching the sequence of deployment. And because there are so many steps involved in that deployment procedure. All right, so in space engineering, a lot of structures, they need to be folded, they need to be deployed on orbit. There's a very critical issue. So sometimes we just don't have enough monitoring capability to know the status of the structure. And also, if something goes wrong, and it is also very difficult to correct the issues. For example, if one structure is not fully deployed, it is extremely difficult to correct that error. So this is something I would like to address. Okay. So I take the all right. So I would like to address this problem and using a different way. So I would like to view the structure as a living matter, right? As a living organism. Right? So I want to make multiple space structures that can behave like human body. Right? So on this left side, I have these. This is the human body, right? So we have some sensors on our skin, and once we feel something, right? For example, if we feel a very hot temperature, right, we might want the muscle would react to that, and the signal would go to the brain, and the brain would beam back some signal to and we can get our hands back, right? So this is how the human body would work. So what I'm doing is to try to make these morphable space structures behave like human body, right? So I would like to have some biomimic multifunctional sensors add on these structures, and I would like to have some actuating materials, active materials on these structures, and I would like to have machine learning or AI to process the data. So in this way, you have a closed loop to feel the external environment, to know the status of the structure, and then you can process the data, and then you can react to the external environment if something goes wrong, if you want to adapt to different status, right? So that is the overall vision I would like to have. So in today's talk, more focus on the sensing part. I will focus on these multifunctional sensors, right? More specifically, all right, so I would like to develop large area, flexible, thin multifunctional skin, artificial skins for this type of movable structures. Right, so I would like to use these artificial skins to have full body measurements for the structure, and eventually these can be used to do actuation. And hopefully these multifunctional skins would just add a little bit of mass and a little bit volume, and without compromising the structural integrity. All right, so there are some challenges. As you can see on the picture on the left side, these are the Palacios James Webb space silicon. They are very thin membranes, and from this structure you can see that is also quite amorphous. A lot of definition is involved in this structure, and the structure is actually quite thin. It's like a piece of paper, and the structure is very lightweight. So if you want to integrate conventional sensors, conventional multifunctional devices, for example, in the picture on the right side, you have these silicon wafer with all these transistors, right? So they are quite rigid and they are quite thick, and sometimes these sensors could be these devices heavy. Right? So now you see the mismatch in terms of mechanical and in terms of dimension. Right? So the many structures in space, they are quite thin and quite lightweight, and current devices, they are rigid, they are thick, and they are heavy. So you see the mismatch. And there are other challenges such as the very harsh space environment, and also you have a lot of requirements on the volume, on the weight, etc. Okay, all right. So to realize my vision and to address these challenges, I took an approach actually outside aerospace engineering, and I like to use these two pictures to show the reason I'm using this approach. And I often ask people, what is the similar things between a baby and a spacecraft? I think first of all, they are kind of fragile. I mean, baby could get sick, and spacecraft, they are very complex system. Something could go wrong. And after I had my baby, my son is 2 years old, I realized that they both are quite expensive. You don't want things go wrong. And the picture on the left, that is a poor baby who is sick, and that is in he or she is in the intensive care, and you can see that a lot of wires, a lot of medical instruments are attached to his or her skin, and these devices are current devices. They are quite stiff. And on the right side, on the picture on the right side, you see the baby on the skin of the baby. He or she has this very soft, very flexible biointegrated electronics. It's just a very thin film, and it can do a lot of things that can potentially replace the instruments on the left side. Right. So these are soft and flexible bioelectronics. They are ultra lightweight, they are very thin, they are multifunctional, and they can adapt to the large definition of the skin. So that is the inspiration I got. Okay, so I took some technology from this field, and then I applied it to aerospace engineering, specifically for the spacecraft structures. All right, so here I just want to give you an overview on some products my group has been doing. This is the first product I would like to show. So here, no, I'm still trying to learn this. All right, so this one, that is the tip spring hinge, right? So that is actually a section of a regular tip mirror, right? Computer tip mirror. So that is very interesting structure. So when you fold it, when you release it, it can self-deploy. And when you fold it into different directions, they could have very different behavior. So actually this type of a tip spring hinge, they use similar structures already in spacecrafts. So this is a structure, and we try to understand the vibration and also the definition of this structure. So what we do is we develop and fabricate electronic skin, artificial skin. We call it the E-skin. We call this E-skin. You can see that on this yellow tip mirror, computer tip, I have these functional devices, and this is the schematic for this electronic skin. So I have a gyroscope and accelerometer, and I have strain sensor. The strain sensor material is reduced graphene oxide mixed with single wall connecting tube. It has a very high gauge factor of 50, and everything is on this very flexible polyimide. And you can also see that we designed this kind of a serpentine wavy shape because it can accommodate that larger deformation. It's just like a linear spring, right? You can stretch it into a very large deformation, right? So we have this design to accommodate the large deformation of this tip spring. So the picture on this side, the picture here, you can see we fold it and then we release it, right? You can see it can self-bounce back to the original shape. And the data here shows the several vibrational modes we got from the accelerometer here. And we compared to the fundamental analysis, and we see quite a good match between the simulation and the experiments. And in the simulation, we have that perfect boundary conditions. But as you can imagine, in the experiments, the boundary condition is not fully fixed. So you will see some difference between the frequencies. But we do get these different rules shown in this finite element analysis. All right, so I present this work to ERWA spacecraft structures community, and oh, sorry, I want to show this as well. So we have some strain sensors, and here we did some folding experiments. So we can fold the tip mirror like that, and this hinge, this folded region can move to left and to right region. Can move to this hand, can move to this end. So this folded region can move. So the strain sensor can tell where the folded region is. All right, this is something also interesting to know in the folding and the deployment of these type of structures. All right, so so I presented this work to the ERWA spacecraft structure community, and there was a researcher from NASA Lani, and he got interested, and he asked me, hey, I have opportunity that could potentially send your work to space, and I got interested. And what he wanted to do is to actually have this kind of E-skin attached to this composite carbon fiber ultrasound deployable boom I just showed it, right? So that is what he wanted to do. I got interested, and I said, hey, I would be very interested to collaborate with you. So this is the boom I just showed you, and it is a bistable boom because this is the first stable state, and when I roll it, like that, I roll it like that. Right, so it can stay in this folded shape. So this is the second stable state. So in this shape, it is locked. I don't need any other mechanism to keep the stored configuration. So the material is very thin, and I have three layers in this computer: a 45-degree plane wave, and a 0-degree unidirectional along axial direction, and also another 45-degree plane wave laminar. And the thickness of the entire laminar is around 160 micrometer. And you can also see the cross section, which is parabolic. So we designed the material and also the cross section so that we can have this bistable configuration. So it can store here, and when we just open a little bit, it can self-deploy without any other actuators. And the entire length is 4 feet long, And that will be a flight hardware installed on a 3U CubeSat. The CubeSat is now being developed by Virginia Tech, and we're going to send that thing to International Space Station next year. All right, so that is the structure, some information about this structure, and then I want to show you some requirements. All right, so we want to add some payloads on this deployable boom, right, on this deployable boom. First of all, we want to deliver power. We want to deliver power from the root to the end, right? So the root would be installed, will be attached to the CubeSat, and when the boom is deployed, right, that will be in space. So we want to deliver power from this end to this end, right? And we want to transmit some data back from the payload to the computer in the CubeSat, right? So we would need to have the power and data lines in the structure, and at least we want to use some digital data transformation I2C protocol, and they define that for us, and we want to embed the power and data lines within this ultra thin composite boom. Remember, the thickness of this boom is only 160 micron, and if we add some lines on the surface of the boom, for example, if the line is even 50 micron thick, we basically add 1/3 of the thickness. And when we roll it, actually that would increase the total volume of the stored structure by 1/3. So actually that is a lot of increase in terms of the volume. So we want to embed the data and power lines within this ultra thin composite boom. And the payload actually used to measure the vibration and also the deployment behavior of this boom, right? So we want to measure all these 6-degree freedom dynamics, the vibration in X, Y, Z, and also the rotation in 3 directions. And we want to minimize the weight and the size of the payload. And as you can see that this boom has really large definition. So the payload must be soft and conformal to this boom with complex shape. And of course, we are going to send this to space. So everything should survive the extreme thermal vacuum condition in space. So these are the requirements we need to meet for this multifunctional boom. All right, so the first difficulty we met was actually the power and data lines. So we need to have really thin line, and the line should be very narrow. So basically the lines should have very small footprint, and it should be very long, at least 4 feet long. So that is actually not easy. We actually tried printing these kind of lines and try to embed in this boom. Actually, it did not work well. And you can imagine when we embed the material in the boom, and that is a composite material. And when we fabricate the composite material, we need to apply large pressure and high temperature to actually cure the composite material. So that is actually not easy. And we turned out there's actually a simple solution to that difficult problem. We overthink a little bit. My student found that actually you can get very thin wires commercially available on market. It's not easy to get, but you can get some. So we found these very thin wires, AWG wires, American wire gauge wires. The gauge is 44, and the diameter is around 50 micrometer, which is right at the border of the maximum diameter we can have for this Philips product. And it worked. And it has insulating materials coated on these thin wires. And then we tried these wires, and they worked actually quite well. So we embed these wires on the middle plane of the boom. So in the middle, there's 0-degree unidirectional lamina along the axial direction, and we embed the wires also along this 0 direction. So the wires would be in that 0-degree unidirectional ply without increasing the total thickness of this laminate. And we do the layup. We lay the wires in the composite, and then we cue the structure in autoclave. And on the picture here, you can see this is actually the payload we have on the tip, right? As you can also see, it's actually quite small, and we have this flexible circuit, and this small black dot that is actually the IMU, inertial measurement unit, which can give us the 6-degree freedom dynamics. And the Virginia Tech, they wanted to have an LED added on the circuit. So once we turn the power on, the LED would shine, and they have a camera, they have an optical camera and also a RR camera, infrared camera, which can take pictures of the payload, right? So this is another small stuff we add to their circuit, right? All right, so as I mentioned, the boom would be rolled and stored in a CubeSat, and here that is the hub that would store this boom here, and so it would roll into the hub, and this is the picture showing the hub from another direction. And you can see that because they need to add some other instruments in this area, and they only have a very narrow space between the central hub and the external case. So that's the reason we cannot actually add some stuff on the surface of the boom. So we have to embed the wires in the boom to save some space. And the data is transmitted to the flight computer using a sleeper ring. Okay, so this part is the hub and also the sleeper ring. Here I showed you. They are just the initial designs. Virginia Tech, they are still developing the final versions for that. All right, so we put the boom in thermal vacuum chamber, and we did some tests, and we found that the baseline are not shifted. So let me show you a video about this boom. We fabricate this boom, and we delivered this boom to Virginia Tech.
All right, so right now the boom is assembled. So I have the IMU right here attached to the thin wires, and the rest of the wire I'm just leaving there because it's backup wires. If anything goes wrong, we can use those wires. And this is right now mounted on a wooden board. I wrapped it in aluminum foil and then tape, so just to make the surface ever so slightly smoother. And on the other side, so these wires are connected to the IMU. I have soldered a few jumper wires so that you can make testings without removing the thing. I've also labeled it. You can see all these writings here. So SCL, VDD, SCA, ground. You should know like where all these wires are going. So for my end, I'm using Arduino to power the sensor and gather in data. This is just a temporary board for the pull-up resistors on this end, and it won't be there by the time I'm delivering it. I'm just showcasing it. So right now, I have not activated the VDD yet, but once I plug this wire in, you should see the IMU, the LED on the IMU turning on. So yeah. So right now, I'll be plugged this in, and that should turn on. So you see the LED turn on, is correctly powering it. Just go to the computer, and I'm hitting the reset button on the Arduino to get the data transmitted. And right here, so now it's gathering all the data. All right, so just for a quick demonstration, I'm not gonna bend the booms or anything else, just to keep it as it is. But I'm gonna lift this up and do a kind of a motion. You should see the values are changing. Right? So you can see as I'm rotating the boom, the values are changing with it on the computer. So, right. So now this is basically ready for shipping, and I'm gonna remove the Arduino. I'm gonna remove this temporary board. So it's just gonna be the boom and with the jumper wires attached to it, and with CM.
We delivered to Virginia Tech. We have some additional wires embedded in the boom, just as the redundancy. All right. I think I have much time. Let me. All right. So these are some tests we did, and we put the boom in the deployer, and we let it deploy, and we let it vibrate, and here it shows the vibration and also the rotation in the time domain, and then we did FFT. We got the mode for the first mode, which is comparable to the finite element analysis we did. All right, so with this said, I just want to give you a quick overview on some other projects we've been doing. So the boom I showed you with a payloads that can measure the vibration, and actually we recently got a 3-year grant from AFOSR, which can support us to develop a more advanced electronic scheme with multimodal sensing capability, including strain, vibration, thermal, UV, and atomic oxygen, which can get us the full awareness of the external space environment and also the status of the structure. And we are going to use machine learning-based data processing to learn the status of the structure and use that to study the structural mechanics in space environment. And we also have a planned product with NASA Langley, which would focus more on the actuation side. I heard that NASA Langley is getting budget cut. My finger is crossed. Hopefully nothing would happen to this product. There are several other products we did. For example, here, we actually did this kind of flexible sensors, which can, let's say flexible UV sensor, which can measure the UV in harsh environments, and we integrated that to wireless circuit, which can beam the data to the data acquisition module in a wireless way. All right, so this is another product, not related to space, but for aircraft structure. So the products I showed you earlier for spacecraft, space structures with this bio-inspired electronic scheme. So this product is more focused on aircraft. We would like to add this bio-inspired electronic scheme on the surface of the aircraft wing, which can be used to measure the deformation and also the aerodynamics. And we also would like to develop this bio-inspired bird bone-like structure. This is the microstructure of a vulture bone. And so we like to develop this bird bone-like ultralight structure, and collectively we can have bio-inspired aircraft with the sensing capability and the lightweight structure, and also the movable capability. So this is another project related to this bio-inspired aerospace structure product. All right, so with this said, I just want to do a quick summary. As you can see that we do movable structures, and we added soft electronics to movable structures to create new multifunctional aerospace structures. And here I just want to give a shout out to my student and also my collaborators. And I would like to acknowledge the financial support from the funding agencies. Thank you very much. All right, good.
Okay, thank you. And next we have Dr. Eric Greenwood from the Penn State Aerospace Engineering Department. He's going to give us a special topics talk from our Rotorcraft Acoustics and Dynamics Working Group. And the title of this talk is Urban Air Mobility Vehicle Noise. Let's welcome Eric.
Thanks. Good morning, everyone. In a minute for this to go up. So first I'll just kind of go through, thank you to Ed Smith for giving me some time to talk about this. Just kind of a very quick overview of what's happening in the Rotorcraft Acoustics and Dynamics group for CAV. And then followed by that, we'll get a little more specialized and I'll talk about kind of work mostly going on in my group on urban air mobility noise here at Penn State. Okay, cool. So let's see if my clicker works. There we go. Okay. Slight time lag. All right. So, of course, the topic here is rotorcraft, right? Rotorcraft are aircraft that have rotors. That's sort of self-explanatory. Right, particularly here, we're interested in vertical lift aircraft and everything ranging from kind of conventional helicopters that you see there in the upper left of this diagram. And as you walk around, you start to get into some of these less conventional configurations that people are looking at today, things like compound helicopters, tilt rotors. And then as we go to that lower right-hand corner, you start to see these urban air mobility vehicles. So the Beta Leah there and the Joby aircraft, which generally have what we call distributed electric propulsion. So they have lots of rotors. And across all of these aircraft, right, these rotors are doing lots of different jobs. Not only are they providing thrust to lift the aircraft up, but they also are the propulsion system, and they're usually the control system too, right? So that rotor has a lot of work to do. And of course, in this group, we are interested in kind of the acoustics and dynamics of these aircraft. And that really covers a wide spectrum. So down to the low frequency range, you're really talking about things like the flight dynamics of the vehicle, the flight mechanics, handling qualities. And it's kind of, we go up to the frequency range, right? We start talking about things like vibrations, the aeroelastic loads and the blade dynamics, up to interior noise and vibration. And then even kind of can extend up to ultrasonic frequencies for things like diagnostics and anti-icing systems. Kind of my area and what I'm going to talk about mostly today is that highlighted in yellow. So that's really exterior noise generated by the helicopter. Of course, if it's noise, we're concerned about the audible frequency range. We're lucky we have quite a range of faculty here with Penn State and through the Applied Research Lab who are working on in this area. And have produced a number of students who are now taking their skills and bringing them out there to industry and government. In addition, we have a really big kind of critical mass of current graduate students who are working in problems all across that sort of spectrum that I showed you before, which is really cool because they can kind of work together and share information. And, we have a big group here essentially working on this area. Just really quickly, this is really just sort of a list of some projects I'm not going to talk a lot about today, but, we are getting some sponsorship here from agencies ranging from the FAA. We have a lot of FAA projects, Department of Defense, of course, and NASA. And there on the bottom, kind of want to highlight, we've kind of recently renewed the Vertical Lift Research Center of Excellence, or VLRCO, and a number of tasks under that kind of larger 5-year project relative that are related to acoustics and vibration. Just kind of quick rundown of some of those tasks. There's one project here looking at prop wing interactions and the resulting noise and impacts on performance. We have this interesting project. You may have heard about this during Mark Miller's talk yesterday, but we're really interested in the scalability of noise generated by these multi-rotor systems in particular. So we're going to do everything here from small scale measurements to full scale, and then really develop this interesting capability where in Mark Miller's group, there's a compressed air wind tunnel, which allows us to match exactly the Mach number and Reynolds number across that entire range. We're hoping they will let us sort of connect the dots between these two scale regimes and then come up with some scaling laws for these multi-rotor systems so that we don't always have to test them at full scale. And another task I wanted to highlight here really is taking some techniques that are used in the flight dynamics world and then applying them to a number of things, including acoustics, in order to give us sort of rapid on-the-fly acoustic predictions. Here, this is just me in stereo. All you really need to know here is that I've been here at Penn State. I'm now in my 4th year. Prior to that, I was at the National Langley Research Center for a little bit over a decade. And throughout that entire time, really the primary focus of my research has been on rotor aeroacoustics. So that kind of leads into specifically what I wanted to talk with you about today, which is a focus on urban air mobility aircraft noise activities that are happening here at Penn State. So really the goal of kind of the program that we're developing here is in order to enable a new class of vertical lift aircraft, in order to be able to operate in and around communities that are increasingly noise sensitive. And we know from helicopters, right? Helicopters are kind of getting pushed out of urban operations because of noise concerns, and there aren't really that many helicopter operations. In order to make urban air mobility work, whether that's delivering your package in a few minutes across town, or even air taxis to deliver people across town, right? We're talking about much larger numbers of aircraft operating. And the only way that's going to work is if we can make these things so much more quiet that the community will accept that. Right. And so what I kind of see to tackle this problem is we got sort of 3 different ingredients. We need to do some experiments so that we can really understand the physics of how noise is generated by these kind of new aircraft systems. Then we want to use that physical understanding in order to develop noise models that are in my case, fast, I hope, and then also reasonably accurate. Right? And the reason to have models that are fast is so that we can use them, right? And that's really what I'm interested in, ways that we can do this modeling so quickly that we can explore new applications, have those kind of models running online. And I'll talk a little bit about that as we get to the end of this. So, this is the stuff that's kind of circles through my head when I close my eyes at night. Right. So these are just a couple of images that show free wake output from CDI's charm code. Just as an example, but if you're an aerodynamics guy like me, boy, you see all sorts of complicated interactions here, right? Between the rotors and other rotors, between the rotors and the struts that mount them, wings in the rotors, and acoustic scattering off of all of these surfaces, right? It's a really complicated aerodynamic and acoustic environment. And, modeling and predicting that complexity is really the big challenge, right? So, these aircraft are a lot different than conventional aircraft. In that you can no longer really treat it as a single isolated rotor. I have to consider all these pieces and their interactions. So let's kind of talk about those 3 different prongs, right? So first with experiments. So we have been doing a number of experiments, both flight experiments outdoors and in our lab. So I'm going to highlight some activities that are going on in our lab. So we have a flow-through anechoic chamber over in the Hammond building. And this is basically a small open jet wind tunnel that runs through an anechoic chamber. You can see the inlet of the flow on the left, and there's a collector there where the outlet of the flow to the chamber is on the right. And this facility was originally developed to do jet noise experiments. Recently, we've been doing a lot of rotor noise experiments. And along with Jose Palacios, we built this test stand that lets us test a variety of multi-rotor configurations. So you can kind of see those pink areas there. Those are where the rotors are mounted. The upper and lower test stands are configurable, so we can adjust the rotor tilt. They're telescoping. We can adjust the separation distance between the rotors. And that lower test stand is actually on rails, so we can slide it forward or backwards in the chamber. So we can put these 2 rotors in any configuration relative to each other that we want to. We also have acoustic traverse. So you can see that vertical microphone array there on the right side of the plot. That is mounted to a rotary actuator, so we can actually swing it around the room and essentially map out a hemisphere or a sphere of noise around our test article. So we've been using this for a number of different things. I want to highlight one example. It's a project that NASA Langley has been sponsoring us to do. They started by investigating the stacked co-rotating rotor concept. So we have two rotors. There's a slight vertical offset between those two rotors, and they are rotating in the same direction. And the initial work at NASA, which showed some promising results in terms of performance improvements and noise reduction, used a kind of a mechanical linkage to couple these two stacked rotors together so they would rotate together. Kind of the unique capabilities that we have, and why they're interested in doing this work here, is we can do forward flight. And then we also, because we have two separate test stands, can get independent measurements of the performance characteristics on the upper and the lower rotor. Now, the challenge with that is that because those rotors are no longer mechanically coupled, in order to keep them in the same relative position or phase relationship with each other, we need to develop a control system that keeps these two small electric motors phase locked, which turns out to be a lot harder than you would think. It took a lot of work to get that together. We ended up kind of developing this kind of two-phase control system to do it. But in the end, the results are pretty good. So if I click on this with our luck, there'll be a little video that says playing. The same relative position to each other. So it took us a while to get there, and it's difficult to do it at this small scale, but now we have this capability, and that lets us look at some interesting things. So for this co-rotating rotor, and I'm sorry, on the projector here, these are kind of small, we'll talk you through it. On the upper set of plots there, we basically have thrust on the left and power on the right. In yellow is the upper rotor, and in the purple color is the lower rotor. Right, and the lower rotor generates less thrust because it's in the downwash of the upper rotor in general. And the black and the lines in the middle are basically the combined total kind of non-dimensionalized by the size of the rotor, right? So that's why it lies there in the middle. And if you look at the upper and lower rotors as those phase angles approach zero, so this rotor system is kind of acting like a biplane, right? You have a big influence effect where the upper rotor thrust increases, right? The lower rotor thrust decreases, and there's a phase angle dependence. And as I move them to like a 90-degree phase offset, this sort of starts to act more like a conventional four-bladed rotor that's coplanar. Right. So if I look at that combined line, if you look closely, right, I get a little bit of an increase in thrust. If I pick a particular kind of stagger configuration between the upper and lower rotors, I also get a little increase in power. And that lower left thing shows me what we call the figure of merit. So essentially, how much thrust am I getting, or how much power does it take me to generate a certain amount of thrust? And again, I get big changes when I look at the rotors independently. When I look at the sum total, it's basically a flat line, right? So, I'll say at first, this is maybe a little disappointing. There's not some, big performance benefit to get by choosing a certain phase angle. But from an acoustics point of view, it's kind of liberating. It means I can choose whatever angle I want and focus on noise. Right, so noise is what's shown there on the right-hand side, and we've done a little bit of an extraction here. The black line there shows the total overall sound pressure level. The green markers are the tonal noise, and that tonal noise reaches a maximum when the rotor blades are essentially acting as a biplane, like a two-bladed rotor, and it decreases and reaches a minimum as I go towards a phase angle of 90 degrees, right, and I start to cancel out the 2 per rev harmonics. Interestingly, that blue line is the broadband noise generated by the rotor, and it almost has the opposite trend, right? So I can get a broadband noise reduction when I have these rotor blades kind of operating in a staggered configuration, and I lose that reduction when I go towards more conventional 90-degree configuration. So depending on the kind of noise and the frequency content you're concerned with, you can kind of control that by adjusting this phase angle. And next, I just wanted to point out, and I think there'll be a talk on facilities later, but we are super excited in the new building under construction now is a new anechoic wind tunnel. It'll be a significantly larger anechoic chamber. What I really wanted to highlight here is the aerodynamic capability for Aeroacoustics. We are going to have a couple of different configurations here for this closed circuit wind tunnel, one for Rotorcraft, one for jet noise, and the kind of flow path here for the Rotorcraft configuration is shown. We're targeting a 3.5-foot diameter open jet wind tunnel where we can hit flow speeds of around 80 knots. So something you can imagine I could put maybe a half scale, maybe a small full scale UAM rotor at a representative operating condition in here. Right, not have to worry about a lot of those scaling effects. And it'll have a proper kind of turbulence management system. We want to get kind of clean flow going through it. So that's something to look forward to in the near future. So a quick run through experiments. So next talk about modeling and predictions. So I'll start first very simple. So a number of you may be aware of the PSU WOP tool. It's developed here by Ken Brentner and his students at Penn State. It's kind of a general purpose Aerospace solver. We have developed some just open source tools that are available to anybody here that have, kind of oriented making it easier to use. So you can use it for some simple conceptual design studies. So we call this VSP to WOP because it couples NASA's Open VSP design tool. We can just sketch up a rotor system like that one shown there in green. And then it automatically does some basic air loads calculations, generates all the inputs for PSU WOP and runs it. And it can do a little bit of post-processing of the data. And that the lower plot there just shows a comparison between predicted and measured pressure time histories for this Boeing Model 360 rotor that was tested in a wind tunnel. And we get pretty good agreement for those kind of simple isolated rotor cases, right? So this is a nice way you can just quickly take a look at some parametric trends. I'll give you one example here. I modeled up a notional eVTOL rotor. If you've been following the industry, it may look a little similar to you. And just did a parameter sweep, essentially changing the tip Mach number or RPM of the noise rotor, and then looking at how the different noise components change. So as you might expect, that thickness noise that drops off really quickly. That's that blue line. The loading noise, you either reduce tip speed, I should say. The loading noise drops off a little more slowly, right? But it still falls off fairly rapidly as I reduce my tip Mach number from like 0.8 to say something like 0.5. And then any kind of unsteady loading, including our aerodynamic broadband noise, which is kind of represented by that red curve, it doesn't really drop off very quickly at all as you change the tip Mach number, because it's so heavily driven by the unsteady time rate of change of the loads, and less so by convective amplification like the other sources. And in the case of broadband noise, because as I reduce the tip speed, I'm starting to ask this rotor to work harder, right? I operate at higher angles of attack. The boundary layers get thicker. I just start actually having an increase in noise with reducing tip speed, right? So there almost for any given rotor sort of ends up being a sweet spot where there's a preferred operating RPM or tip Mach number, where you're going to generate the least noise, right? It's not just lower speed is always better. And I think not entirely coincidentally, this range where we find an optimum 0.4 to 0.5 tip Mach number happens to be where a lot of UAM aircraft also operate. Okay, now that simple system again doesn't predict complicated aerodynamic interactions. We need to do that certainly to understand what's happening with these multi-rotor vehicles. But the big problem is with all of these rotors, the computational complexity increases really quickly, right? So modeling those kind of rotor wakes is a n-body problem. So typically it takes order n-squared operations. And if I have tens of thousands of vortex filaments per rotor, and I have lots of rotors, this gets expensive really quickly, right? And it becomes difficult to do things like conceptual design when you have to wait hours to get answers for a small configuration change. So we wanted to come up with a faster way to get a good enough answer. And so we developed a new wake model. We're calling it OpenCopter. That's kind of based on some different potential theory approach where we don't have direct vortex-vortex interactions. And it turns out that works fairly well for most circumstances for these multi-rotor aircraft. This has been coupled to PSU WOP, and we're working towards an open source release. We have a few external beta testers now. In a few months, we hope to make it available to everyone. There aren't a lot of good acoustic comparisons here for these kinds of rotors, but for multi-rotor systems, I do want to give you one example here for this reference case we use a lot in the kind of helicopter world, the Hard 2 experiment. There's a model BO5 rotor you can see there in the DNW wind tunnel on the left, and they had a rake of microphones that surveyed the noise underneath that rotor in a blade vortex interaction flight condition, right? So where the rotor is interacting with its own wake. So you can see here, when we look at the carpet plane of BVI noise, our measured results on the left, or our predicted results on the left, agree quite well with the measured results within about 2 dB across all directivity angles. And we matched also the directivity pattern that was measured in the experiment quite well. So we believe our wake model is doing a pretty good job here, and when coupled with the acoustics to resolve these interactions. Kind of going into more detail, we're also looking at how much flight mechanics interrelates with acoustics. So we have some projects where we're coupling a flight simulation for DEP aircraft called DepSim, developed by Joe Horn, with CDI's charm-free wake model in PSU WOP-WOP in order to predict the noise of these vehicles in unsteady flight conditions. So I'm going to show you some examples for this kind of notional eVTOL vehicle. It's a lift plus cruise, got 4 lifting rotors, 1 pusher prop, and a wing. And we'll take a look at a couple of different flight control schemes that you can apply to this vehicle during kind of low speed transitioning flight. So in this example, I'll show you a low speed maneuver. We're just doing a roll doublet. So roll 5 degrees to the left, then switch and roll back 5 degrees to the right. Flight path ends up looking like that blue line on the right. So a little slow, kind of gentle slalom maneuver. And over here is a basically on the right, we show the variations in either RPM or in collective angle, pitch angle for one of the rotors during this maneuver. And then the plots on the lower left are showing the change in noise for different observer angles. For both on the far left, the variable RPM case, and kind of there in the center, the variable collective pitch case. And what you notice is for the variable RPM case, it's kind of intuitive. There's a lot more variation in noise, right? The range of change levels is higher than it is for the variable collective case. You can also see some spikes where the kind of the controller gains are kind of high as you initially enter that roll or leave it. So you could adjust those in order to get, probably reduce some of the noise in those cases. And we have a few papers that look in a lot more detail about what's going on here, but clearly the control system has a big impact on the noise of this vehicle. Finally, I kind of wanted to wrap up by talking about operations, right? How we can use this stuff to make UAM aircraft operations quieter. So we've developed a code here called PSU NiceOps that lets us do accelerated noise predictions for operational conditions on the basis of either pre-computed acoustic data that comes out of our models or from even flight test measurements. So in this case, I'm just going to apply it to a helicopter because we have lots of good measurements for that. There's an S-76 helicopter. And so whatever I do, I can do this offline. I basically am going to generate a database of acoustic hemispheres like that one on the left that describe the frequency, magnitude, and direction of noise. And I'll generate that for a sequence of different flight conditions. In this case, a 3-dimensional database of basically representing speed, thrust, and flight path angle on the vehicle. Right. Once I have this database, whether it came from measurements, it came from computations, I can then apply it really quickly online whenever I want in order to predict the noise of any arbitrary maneuver. Right. So here it just shows some ground noise footprints. The top one is measured. And so those little weight markers there represent the actual microphone locations. And of course, we can only measure the noise where we had microphones. So that contour is kind of limited. The lower plot is showing the predicted ground noise contours for this approaching flight condition, kind of a decelerating, quite complicated low noise approach procedure. And the modeling tool does a really good job recovering what we saw in that experiment, even though the model is based on steady flight measurements and the actual case we're predicting is maneuvering flight. So we've now been applying this kind of modeling approach in order to develop low noise operations. So one project we had not too long ago, we coupled this with unmanned traffic management system that's been developed by another Pennsylvania company, OneSky. And in order to do some acoustic planning for UAM aircraft and UAS. Or drones, basically. So that upper plot shows a nice little movie of some UAM aircraft that are flying around, where we predicted the noise kind of in the LA aircraft area. And then we also did some work on if you have some objectives, say for package delivery, right? How would you route those aircraft so as to reduce the noise impact using some optimization schemes? And that's kind of what you're seeing there on the right are sort of optimal low noise flight paths for UAS, considering all sorts of things for safety and performance and demand in the DFW region around Dallas-Fort Worth. So, that kind of gives us a good start. We want to increase this use of autonomy and eventually get things to run quickly enough so we can actually have them on board the aircraft. So when things change, right, the aircraft can respond intuitively right away. We don't have to follow some pre-planned flight path because everything is sort of time dynamic. The challenge that we have here is that our good methods, which are quite fast, could be faster than real time. It's still too slow to put an optimizer around them and come up with optimal low noise paths online, right? We can make some approximations, right? We can, that kind of upper diagram is showing, we can divide this up into like a combinatoric optimization and run like an A-star method on it to accelerate it. That'll give us an answer faster than real time that's optimal in some sense, but often gives us kind of weird results that might be impractical. So the lower plots there just show some kind of dynamically replanned flight paths where that blue section of the airspace was suddenly closed. So the vehicle has to do a rerouting, say over a 40-kilometer distance. The one on the left shows one where you can kind of take your time to do that. And you get a nice smooth flight path that kind of makes sense. You take off, turn at high altitude, come back down and then head towards your landing zone. The right-hand one shows one where you have a time constraint. You say, I need to hit this answer in like the next second before I hit sort of the next waypoint in my trajectory. And you start to see now we lose optimality, right? I'm starting to, the aircraft has this almost serpentine pattern that's sort of constrained by the structure of that optimization, which isn't very practical to fly and is a bit noisier too. Right, so kind of what we're working on now, this is on another VLR project, is to develop a new approach where we're going to use a hierarchy of methods in order to solve this problem. Right, so we'll use those cheap methods, and I'm going to kind of call that exploration, to search over a wide area and try to find some promising candidate low noise paths. Right, maybe the criteria is just stay away from where people are. And then once I have those paths, I can use a more detailed optimization. That's where I'm calling it exploitation, to really optimize the details of that path. Right, and because I've constrained the space that I'm going to search over, I can use a little more detail in my modeling and get more of this physics. And then an even closer level, right, I can call this adaptation. The aircraft itself can be thinking about, I have this optimal flight path now. How do I fly it? How do I use my effectors? All these different rotors to move that vehicle down the path in the quietest and most efficient way, right? So I kind of have that different hierarchy there. And then on that top level, we can think about aircraft operating in isolation. Well, if they all choose to do the same thing, right, then I'm going to be flying over some poor family's house all the time. Right, this happens with low noise air transport routes today, right? And it's not really a fair or optimal situation globally, right, for the operations of all the aircraft. So we may need to come up with some schemes in order to allow these aircraft to coordinate. So one sort of thought here, and this is sort of this video, is what if instead of thinking about things like a day-night level that are calculated over a day, I think about how the fleet of aircraft could be laying down noise in space, right? And then instead of just calculating on a daily basis, I apply some time constant. So I add noise as the aircraft flies over, and I kind of take noise points away slowly over time, right? Then I can, as long as these aircraft sort of share a ledger of where the noise has been deposited in space, they can use that to route around things in the future and kind of naturally avoid, constantly flying over the same place and thinking they're all on the same optimal route. So just to kind of wrap up, right, emphasis a lot of the work that we're doing right now is on multi-rotor eVTOL because they're bringing lots of new challenges. So urban air mobility aircraft and UAS. We do have some continuing helicopter projects as well. We're really lucky here that we have kind of a critical mass of students working in all areas of rotor aeroacoustics. So I kind of counted about 15 students working mostly between myself and Ken Brentner on rotor noise in particular. And the cool thing is it's across a wide range of areas, right? Everything from experiments, predictions, to operations, which I think is really complementary, right? We can, a student who's working on some theoretical modeling can work with somebody else to collect the validation data that you need, and that can be help support and validate the model. And sometimes when the validation doesn't work, you can sit down and think, well, what am I missing? What are the physics that are really important here? And then, of course, we're looking for applications, right? We want to use this stuff to make the world a quieter and better place. And I hope here, obviously there's a lot of depth. Our group is focused on rotor aeroacoustics, but in that kind of niche, I'm hoping we have a full spectrum of different things from theory to experiment, and everybody sort of comes away with a good broad understanding of all of that. So with that said, thank you very much for the opportunity to kind of share what we're up to, and I'm happy to answer some questions.
Thanks for a great presentation. I noticed an absence of the examples of ducted props in your presentation. When you're running quadcopters that you sacrificing efficiency, you can effectively have noise control using. So, what are you considering ducting?
Yeah, it's a great question. It's ducted rotors are really hard for us to model, right, for various reasons. We're actually going to be doing an experiment in about a month where we're going to look at a small ducted rotor in our anechoic chamber and at least collect some baseline data there. And in particular, in that case, we're interested in turbulence ingestion. Right, so we're going to be looking a lot at turbulence ingestion noise. So it's definitely on our radar. It's difficult, and so we don't have the modeling tools yet to kind of fully solve everything. But we sure would be interested in developing them. All right. Thank you very much.
All right. Good morning again, everybody. I'm going to give you an update on our AI and ML working group. So as you may recall, a couple of years ago, we put together a roundtable discussion about applications of artificial intelligence and machine learning in acoustics and vibration. And this spawned then another working group. And we pulled in people from a lot of the other working groups on campus within the CAV, but we've also been able to reach out to some people who hadn't previously been, CAV collaborators, but who are working in the fields of AI and ML, which, as everybody knows, have just been booming in terms of both the research that's going on and the interest in AI and ML as tools in engineering and other sciences. Let me just quickly talk a little bit about the missions and the goals of the working group. So the leads for the working group are myself, Karl Reichard, and Huang from Aerospace Engineering. Danny will be here later today. He wasn't able to make it this morning because he has a class to teach at 10 o'clock. So we're looking at physics and data models and how we can use artificial intelligence and machine learning to basically make more robust models that are explainable and believable. Now, there's a lot of skepticism from people as they start to use AI and ML because a lot of times they seem like a real black box. And when you do have demonstrated results of these models, you can show how well they fit, but it's not always clear how they work. And in engineering, because a lot of our engineering work is tied to physics and we have to be able to explain that, that's really a common theme in a lot of the projects that I'm going to describe for you. In addition to this, as with a lot of our goals here at Penn State and within the CAV, we're trying to train people, build these packages that people can use, and identify best practices. So we're trying to bring together people from a diverse set of applications and develop some tools that we can then share to really speed up the development of AI and ML solutions. So some of the research areas are reduced order modeling of multidisciplinary dynamic systems. I'll show you a couple of examples of that. Data augmented design and optimization. Then a lot of that goes back to our reduced order modeling, what we call feature engineering and extraction. These are the metrics that we can pull from our data that can be then used in decision making, and particularly feeding into classification and pattern recognition problems, which is one of the areas that I work in for machinery health monitoring. Looking at how do we use these, high dimensional tools and models to combine multifaceted and multivariable information into kind of a single prediction or inference. And then there's also a lot of focus on verification, validation, and uncertainty quantification. So we have a lot of systems with a lot of uncertainty in them, both in the system model and in the data, and trying to use machine learning to reduce that uncertainty. And then again, the theme of data-driven predictive analytics and decision-making. We have a lot of members in the group, and I know we're not showing everyone here just because it's hard to keep track of everybody. A couple of notable additions or changes to the group. Dr. Ashwin Ranganathan is going to be a new professor starting at Penn State in January. So he's joining the aerospace engineering program and has a lot of work going on in uncertainty quantification using machine learning. And now Dr. Damien Jean-Pierre Rouault, he finished his PhD this summer and is now working in industry doing machine learning. So again, this feeder responsibility that we have to provide educated students to work with our industry partners as well. So I'll just highlight a couple of the projects that are going on among members of the working group. And I encourage you to go to the website and download the latest annual report. There are usually one-page write-ups on each of these projects with references that you can then go and get additional details. This is a project by Costas. It's deep reinforcement learning based decision-making and control under uncertainty. All right. So what does that mean? What Costas is looking at is very large scale engineering systems and trying to detect degradation in the systems and then predict what the outcome of that degradation is. Now, the term engineering systems is intentionally broad because these techniques can apply in a lot of different domains. So transportation networks, air fleets, industrial machines, or power generation networks. And the idea is he's using Markov process modeling in these large networks to try to deal with the challenges of incomplete information, no complete system model, and uncertainty in what the cause and effect is. So by looking at the data and building these models and running through lots of iterations of the models to converge on one that fits the data, that's really kind of the common theme in a lot of these machine learning applications, is we now have the computational infrastructure to build these very high dimensional nonlinear models and run through the different iterations to train those models to fit the data. This is something that we weren't able to do 20 years ago with our computing infrastructure and our understanding of how these models worked together dynamically. Another project from Dr. Puneet Singla is looking at system identification and feedback control design for guaranteed performance. Now that, those of you who are, oops, sorry, didn't have the right back button. those of you who are coming from a control systems background, you might initially look at this and say, okay, well, this is what we do, right? We try to identify the system and we design a feedback control system around that. One of the problems is that we have a lot of systems for which we have the real system, we have experiments, and we have input-output data. And one of the limitations we have in terms of designing feedback control systems has always been something called controllability and observability, which means that you can look at the inputs and you can look at the outputs, but you can't build a linear time invariant model that fits that data, because you've got internal states of the system that either are not controllable in a linear time invariant sense from the inputs, or which can't map to those outputs from an observability standpoint. And so the idea here is to really use nonlinear system identification by building these neural network models, which are inherently have these nonlinear activation functions, which now lets you get past the limitations that we have with some of the linear models. So we're not really changing the laws of physics or anything, we're just building a different kind of model. But now at least we have a nonlinear model. And those of you who have done control theory know that one of the first things you do when you have a nonlinear system model, you put some feedback control around and you try to linearize it around your operating points. But now you have that internal model that we can use for the feedback control system design. Another big area within the application of machine learning in engineering systems has been reduced order modeling, and this is really one of the focus of Dunning's work. And a good example of this is where we have, this kind of problem where we have a source and we have a bunch of receivers on the surface, but we don't know how to map the waveform information to get to the source. But we can describe it by a partial differential equation. And what that does is it puts some constraints on the structure of the neural network so that we can map back to some explainability. So we know has to be a model for the system. We don't know what the model parameters are. So we use the tools from machine learning to learn those model parameters, and the underlying model that we're using encodes the physics of the situation so that the system, so that we can then go back and look at what did the machine learning model learn, and how does that overlay with the model that we have, right? Another project that Deming has ongoing has to do with the with modeling the thermal elasticity of materials used in hypersonics. So hypersonics is a very big research area now in engineering and particularly in the government, and also for things like supersonic flight. And so these models take a long time to run. And so with the traditional finite element modeling approach, it might take a week of computer time to generate the results of the model. We then use neural networks to learn a reduced order model of the system, which is going to focus on the most important data points or aspects of the model. And then with the machine learning model, we can then regenerate new points. And new data that we generate is on the order of seconds instead of weeks for the model generation, because it's just a much lower order model. Right, and that same approach will work for other types of topologies. So here we have an example of one using what are known as graph neural networks. So again, graph neural networks impose a little bit of a model structure on the system in that we have nodes in the system and they are interconnected and have actions between them. So Again, once we learn the graph neural network and we can go in and we can assign meanings to what these nodes are, and we understand the kinds of interactions that are going on between the nodes, that fits with our physical models. What we often don't know is the strength of the connection between nodes, or connections between nodes that we did not realize were there before. And these can lead to some interesting insights in the models. The one on the left shows a power grid, and it shows voltage levels across the power grid. And so this was the true measurement model, and this is the result of a prediction of the evolved state of the system. You can see good agreement there. But the same type of approach will also can also apply to other graph type networks. And the map that you see on the right represents applying the same type of approach to weather prediction, where the nodes here are measurements at different weather station locations. And the goal of the model was to look at past weather data and then do a like 3-day ahead prediction of the evolution of those temperatures. So the kind of thing that you see on your weather report, where they show you the map across the United States and they say, okay, here's what it looks like today, here's what it's going to look like, you know, on Thursday and Friday and for the weekend. Right. So the next two projects are ones under the leadership of Dr. Greg Banier, who is now at the Applied Research Lab and is one of our collaborators in the AI ML group. So I'm going to turn the rest of the time over to Greg to talk about two projects that he has going on. Greg, thanks.
All right. Yeah, thanks. Yeah, hello. So whenever we're talking about machine learning and artificial intelligence models, oftentimes a question that one can reasonably pose is, how can I trust the result that's coming from this model? They're by nature black box models. You have a mapping of inputs and a mapping of targets or outputs, and you're mysteriously somehow trying to establish a mapping between those. And so the question then becomes relevant, having to do with verification, validation, and uncertainty quantification. So I'm interacting with some people across numerous universities, industries, labs, and so on in the context of ASME, where we've put forth an example problem that we're basically trying to promote to the engineering community to look at this example problem and see, can we benchmark machine learning models against this? So what we took was a fairly simple problem. It's a tapered cantilever beam in bending. This problem has been studied in the domain of V&V for computational solid mechanics. And so we chose this problem in a way of sort of establishing common ground between people doing solid mechanics and people doing machine learning and AI. And I took this model, just wrote up a MATLAB script, and generated a number of realizations of a plausible beam in bending subject to elasticity parameters and so on, so that we can then take a data set that looks like this. I think it's only about 4,000, 5,000 lines, 6 features and 1 predictive variable. But even with a data set that's seemingly as manageably sized as this, you can take any number of different types of machine learning modeling approaches and develop different sets of predictions from those. So it's like, you know, which one's right? And so that's an area of research. It's an area for which there are some open questions to be asked. So imagine we're handed a black box, 6 variables, 1 output. It could be anything. So here again, we're just using a cantilever beam as a typical sort of example. It could be acoustic related. It could have thermal relationships, any sort of other physics. And you're handed this black box and you don't know how it's made. There's some questions one could pose. You know, what's the evidence that we have? You know, what evidence can substantiate our belief in the credibility of this model? What would that evidence look like for a specific model in one's domain of application? And can we somehow render a machine learning model that is relevant to the physics of interest unbreakable in some sense? So that's a set of questions that we're honestly in the process of exploring. We're building different types of machine learning models. At ARL, we're looking at problems that are not just simply beam and bending, but looking at, for example, vortex-induced vibrations, acoustic structure interactions, and asking similar sets of questions for how we can establish credibility for those types of machine learning models. A related topic to that is the notion of digital twins. And this is, in some sense, building upon work that we presented last year at the CAV meeting. But when we talk about verification and validation of machine learning models, oftentimes those machine learning models can then manifest themselves as digital twins. So a computational representation of some physical reality. And we can say, for example, we know something is truthful about the modeling, but how do we then take what we know to be truthful and kind of cascade it up this diagram into situations where we're doing such objectives as condition-based maintenance, lifecycle management, robust design, and so on. And so we're putting some thought into how we can most appropriately orient digital twins to suit those sorts of objectives. One example of that, and again, this is related to work that was presented last year and work that I did when I was at Westinghouse in the nuclear power industry before coming to Penn State. But we built a digital twin model to represent degradation within a nuclear reactor subject to flow-induced vibration, in which case thermal shields were being damaged. And so this is just illustrating some work where we combined not only data that was acquired from a reactor environment, but also some simulation-based models of the vibrations to combine data-driven modeling and physics-based simulation into a holistic digital twin that's then being used for structural health monitoring at some nuclear power plants. So going forward, this is a diagram that I believe Danning assembled, but I find it to be quite illustrative, that we can look at where are we ultimately heading. And this is certainly true of where we're heading at Penn State, but I would argue it's probably true of the machine learning community in general. You know, we're wanting to move beyond things that merely describe a situation and provide knowledge, but we want to move beyond that to cases where we observe something that's questionable and we want to diagnose what actually happened. And if we can then credibly diagnose causes for certain things that we've observed, then ideally we can prognosticate. We can predict what will happen in the future. And so as the maturity of our analytics increases, we then approach a greater point, or a point at which we can more objectively arrive at decisions without relying so much upon human input. And if we can make credible decisions that we can defend, those then become actionable and therefore more meaningful in engineering contexts. So with that, I'll close out our machine learning and AI talk, and either Dr. Reichard or I would be happy to field any questions that you have.
On the first example you gave, I think Costas with the engine, can you give us some examples of what kind of data you're looking at in large systems? I mean, what are you measuring and what are you building your systems on? Yeah. So thank you, Gary, for the question. I can't really comment on the systems that Costas is monitoring. I know he was looking at some industrial plant systems, so large electrical grids, and he was also looking at large structural models. But for some of the work that we're doing for things like supply chain for the military, you know, we then have everything from sensors that are on vehicles to vehicles that are moving around. You know, they're then connected to units. Units are connected to larger organizations. And then you have a whole nother kind of shadow organization for the logistics and supply chain. And so, you know, a lot of times the connections between those are evolving over time. And those are the kinds of things that have to get identified in the model and then updated.
Yeah, so for the machine learning For the machine learning credibility assessment study that we've currently put forth in the context of ASME, that is indeed a statics problem. But that said, there's some work that is not yet published that we're working on here at Penn State that certainly is dynamic in nature. Primarily frequency dependence at the moment, but I think we're moving towards transient.
Yeah, and I think you bring up a good point, Gary, which is, you know, one of the challenges I think that we're addressing now in machine learning is how do we combine both spatio and temporal connections in the systems. So, you know, the one approach in structural is separability of the partial differential equations into kind of a spatial dependence and a temporal dependence if you take a modal approach. But it's not clear that when you have these large interconnected systems that you can easily, you know, break it up into kind of a model for the spatial dependence and a model for the temporal dependence. Because if you look at particularly like the supply chain models, things are moving around. So the spatial dependence is changing in time, as are the conditions at the different nodes in the network. All right. Well, we have time in the schedule now for a 30-minute break. So people, please, you know, have a chance to chat about the work that's going on. Stretch your legs, get some more coffee, and we will reconvene at 10:30.